Okay, welcome everyone to AMATYC's 2021 webinar series. Today's webinar with Christine Franklin is K-12 Statistics and Data Science Guidelines Impacting College Courses. This webinar is sponsored by the Joint Statistics Committee of AMATYC and ASA and the AMATYC Teacher Preparation Committee. Any views expressed by the presenter are not necessarily the views of AMATYC, and any commercial products mentioned are not endorsed by AMATYC. McGraw-Hill is the sponsor for the 2021 AMATYC webinar series. If you are not a member but would like to be, please consider joining AMATYC. You'll get announcements about webinars and other things that are going on in AMATYC. We are on Facebook at AMATYC. We do have other professional development opportunities. The conference later this year, hopefully we'll be able to be in Phoenix. And then the conference next year, 2022, will be up in Toronto. There are other webinars coming up and traveling workshops. And the recording of this and other past webinars can be found on the AMATYC website in the webinar section. All right, so I will stop sharing. Christine, if you would go ahead and share your screen. And while you're doing that, I will introduce Christine. Chris Franklin is the ASA K-12 Statistics Ambassador, an ASA Fellow, and a UGA, University of Georgia, Emerita Statistics Faculty. She is the co-author of 2 statistics textbooks, chair for the ASA policy documents, Pre-K-12 GAISE Statistical Education of Teachers, co-chair for the Pre-K-12 GAISE II, and writer for the NCTM policy document, Catalyzing Change. She is a former AP Statistics Chief Reader and a Fulbright Scholar. She is crazy about running, hiking, scoring baseball games, and reading mysteries. The floor is yours, Christine.
Okay, thank you so much. I'm going to stop my video while I'm presenting, but I will be sure and turn it back on once I have finished presenting. And hopefully you've got are my slides showing just fine? All right, fantastic. Well, Pat, thank you so much for that wonderful introduction and for inviting me to share today with everyone here on this webinar. Let's see if I can get this to, there we go. Here's a brief outline of what I hope to talk about today in the webinar. First of all, I want to talk about the connection between K through 12 and post-secondary statistics and data science. I then want to give you some examples from our new pre-K through 12 GAISE II document. And then I would like to emphasize with these examples how GAISE II is talking more about using non-traditional data and promoting the spirit of data science at the school level. And finally, just talking about how important it is that our college courses in statistics think about what's happening with the school level statistics. Especially this past year, the global community is being called upon to process and make sense of an enormous amount of data, from screening test results and risk analysis regarding vaccines, to statistical models predicting numbers of cases, deaths, hospitalizations, time to herd immunity. Data is also being used to recommend best practices to combat the spread of the virus. Meanwhile, data is called on to address other global issues, such as climate change, the economy, elections, and social justice. Surely, I suggest, it should no longer be optional for our school-age students to develop statistical reasoning skills. It should be mandatory that all students leave secondary school prepared to live and work in a data-driven society. So today we're going to talk about the guidelines for assessment and instruction in statistics education. And we're going to focus today on the pre-K through 12 guidelines. Now, many of you may be familiar with the college guidelines. The college report was first published in 2005 and more recently updated in 2016. Here are the recommendations from the college GAISE report. These are actually the same recommendations that were made in 2005, but there were two updates. The first recommendation is to teach statistical reasoning, updated with teaching statistics as an investigative process called the problem-solving process, and to give students experience with multivariate thinking. Focus on conceptual understanding, integrate real data with the context and purpose, foster active learning, use technology to explore concepts and analyze data, use assessments to improve and evaluate student learning. Now, also in 2005, the original pre-K through 12 GAISE report was also published. And as you can see, one of the statements from our original document talked about the importance of every high school student being able to use sound statistical reasoning. And I think as statistics educators, we all embrace this vision that was stated in the original document. This document provided a research-based framework that drew on decades of work from many in statistics education internationally. It was a seminal and a visionary document that advocated the necessity of data and statistical literacy beginning in the earliest grades, not just at the post-secondary introductory level. Many of the concepts and skills recommended in this document are part of the current introductory statistics course, and they complement the college GAISE guidelines. This is your framework. The framework was structured as a two-dimensional model defined by the process standards of the statistical problem-solving process and three developmental levels that we called A, B, and C. Now, these three levels are roughly equivalent to elementary, middle, and high school at the school level. We purposely, though, named them A, B, and C because the writers recognize that the levels are experience levels, knowing that many students that may be in an AP statistics or a college introductory course are needing to start at level A, depending on their prior experience in earlier school grades. The pre-K through 12 GAISE I document significantly impacted the inclusion of statistics standards at the state and national level, specifically the Common Core standards in the United States, and it has also impacted other countries internationally. In fact, there is now a Spanish translated version of the GAISE framework. When the pre-K through 12 GAISE I was published 15 years ago, the focus was on traditional data types, from both quantitative to categorical variables, and study designs using smaller data sets of samples from a population. This has also been true about the introductory statistics course content. Today, however, we now know that data sets are vast and readily available. More than ever, we must help our students beginning at a young age to become data savvy, whether working with small data sets or large, messy data sets, traditional data or non-traditional data, such as photos, sounds, images, text, primary or secondary data. Students need to recognize how data is generated, much by them, and the ethical use of data. So the pre-K through 12 GAISE II framework incorporates enhancements and new skills needed for making sense of data today, while maintaining the spirit of the original GAISE. Core to the GAISE II document is still the statistical problem-solving process, although we did have some slight tweaking to the wording. We now talk about formulating statistical investigative questions. And instead of just collect data, we now talk about collect, consider the data. And then, of course, analyze the data and interpret the results. For example, with the immense secondary data that is now available, considering not collecting the data might be the first step in the process. Especially given the computational ability now available, as stated in GAISE II, it is critical that statisticians or anyone who uses data be more than just data crunchers. They should be data problem solvers who interrogate the data and utilize questioning throughout the statistical problem solving process to make decisions with confidence, understanding that the art of communication with data is essential. From 2005 to now, more research has occurred in statistics education, and data have expanded and evolved. The updated GAISE II accounts for these changes while highlighting needed skills. Several of the updated examples have a science focus, and we address using technology where possible. There are over 20 detailed examples in GAISE II. Today, I hope to illustrate all the stated enhancements, but particularly focusing on using non-traditional data and/or secondary data, and questioning throughout the statistical problem-solving process. We will see that as we go through examples, two types of questioning will occur: question posing and question answering. So here is the framework. Keep this in mind as we go through our examples. So we want to first talk about what we would call a level A example. Even at a young age, GAISE II promotes that elementary students are being presented with data in non-traditional forms and learning how to question and make sense of that data. One of the new, more science-focused examples in GAISE II is about ladybugs. Suppose students in an elementary class have been reading a book or books about ladybugs. They notice that the ladybugs illustrated in the books vary in size, color, and number of spots. They wonder what a typical ladybug looks like. So how might the students investigate? And I might mention, this is probably my favorite example from GAISE II. There are places where teachers can order live ladybugs for this investigation, but an alternative is for the teacher to assist students in searching the internet for photo cards that allow students to observe a variety of ladybugs. Now here are photos of the Asian lady beagle, one of the most variable species in the world with a wide range of color forms. How might students make sense of these photo cards to investigate what a typical ladybug looks like? Now, I also wanted to show you they could use something like an artist rendition of ladybugs. So with beginning students, teachers might provide more guidance when coming up with a statistical investigative question, what we call the overarching question that begins the investigation. Now, this is an example of question posing. A statistical investigative question could be a summary question, like the first two questions that are posed, or a comparison question, like the last question that is posed. Now, let me go back to the ladybugs. Collecting data requires careful measurement. So for even young students, it will be important to wrestle with the question. For example, what is a spot versus a blemish? The class may define the difference between a spot and a blemish and might decide not to count spots that are on the margins of the elytra, which is the hard wing cover, Or what if they have a photo that is not clearly focused? Do they attempt to use or discard the photo? Young students need to be exposed to messy data, letting them wrestle with how to make sense of that messiness by interrogating the data. Now, this is an example of what we call question asking. So in the collect consider stage of the statistical problem solving process, beginning level A students might look at just one variable, like the number of spots. More advanced level A students can consider multiple variables like the color of the ladybug's body or the color of their spots. Data collection questions, and this is another example of question posing, need to be developed with the aim of collecting the information that will begin to answer the statistical investigation question. Students can use data cards to organize the variable values for each ladybug picture, where each data card represents a case. Now, a case is the ladybug picture. A data card in this slide is shown above the table. There are 2 data cards here. These physical data cards can assist beginning students to develop understanding of what is a case, which is a challenging concept even for advanced students in the college intro course. The student can also use the back of the individual photos to create the data cards. Here we have one ladybug in a photo with 6 black spots and a red body, and another ladybug in a photo with 10 black spots on an orange body. The student might then next create the table, as shown in the slide, above to identify the variable values for each photographed ladybug. Now, after the data is gathered, it's useful to graph the data. Beginning level A students might use a picture graph, for example, using the actual photos that allows each ladybug to be identified. But as students advance, they can use a more abstract graph, such as a dot plot. Teachers should support level A students in thinking about the distribution and asking analysis questions about the distribution, which includes understanding the median as a middle value, describing the variability in the distribution, such as describing the range. As these analysis questions are developed and answered, they aid in answering the statistical investigative question. Teachers should encourage the level A students to state their conclusions in terms of the sample, but then the students can begin to think about the feasibility of inferring to a larger population of ladybugs. Here we conclude, among other things, that ladybugs in our sample with a red body tend to have more spots than a ladybug with a black body. The students are reminded that these are the species Asian lady beagles. We might then say, how would you feel about inferring this conclusion to another species type? Or we might have the students begin informally reasoning about classification, a key data science objective. For example, we might ask, for the Asian lady beagles, if I picked one of the ladybug cards out of a hat and it has 6 spots, what color do you predict it will be? With teacher guidance, young students at level A were able to use picture cards of ladybugs to begin investigating characteristics of ladybugs and to begin experiencing the role of questioning throughout the statistical problem solving process. They posed statistical investigative questions. They asked questions about how to precisely measure for collecting the data. They posed data collection questions, and they asked analysis questions. And they began recognizing that new questions develop throughout the problem-solving process. A reminder that the statistical investigative process is not linear. As students transition to level B, we want them to become more independent, exploring data sets on their own, such as those composed of photos. Dollar Street is such a data set. What is Dollar Street? Well, Dollar Street is just a wonderful website. And Dollar Street represents the following for us. It represents that data can be used to understand pressing issues that are relevant to the world's population. It represents that data can be large and complex. It represents that data can be manipulated through apps and online interfaces, where sometimes one does not have access to the actual raw data. And it represents that pictures as data are increasingly more common as picture taking is now more accessible through our phones. So Dollar Street is the creation of Anna Rosling. And Anna Rosling is the daughter-in-law of Hans Rosling, who many of you may connect with the Gapminder website, just another fabulous website. And Anna's goal in creating this website was to try to answer this question: how are people's concepts of family and living spaces similar or different across the world? So we use pictures collected at Dollar Street to try to help answer this question. Now, this was the data collection method that was used. Families across the world were asked to volunteer. A photographer then spent the day with the family. And the photographer would take approximately 150 photos of each family and their living space. Now here is, if you just Google Gapminder, Dollar Street, or you can go directly from this link, you will find the photos. So let's go now and think about this concept of family. So as my statistical investigative question, we might have a level B student think about, what does the typical family photograph look like as they explore this website? And I've pulled a few photos here for you on this slide. Now you will notice they're from all over the world. You might also notice that there's a dollar amount in each of the photos. So interestingly, what I would always do with the students is I would encourage them, as soon as they get the photos, to answer these two questions. What do you notice? And what do you wonder about these photos? Well, as I mentioned, one of the first things that I noticed was these dollar amounts. And I'm curious as, I wonder what they represent. Well, if you go to the website, you'll find that they give you a fancy formula. And these dollar amounts represent an estimate of the monthly consumption per adult living in the living space expressed in terms of US dollars spent. So kind of a long-winded way to say, this is a way to give you a sense of the income that the family wealth for each of these individual families. So what do you notice? What do you wonder? Well, what would we hope that students would do with these photos? Well, we hope that they can then informally start making statements about what they're noticing from one family photo to the next. Now, you'll notice that I put a few bullets here on the slide of things that I noticed. I noticed that family sizes vary. I noticed that some families include an elder generation. Some families do not have children. I felt that I seemed to notice that all the families seemed at ease, for example. But we want students to informally explore, notice, and wonder, and pose investigative questions, and then try to informally answer those questions by observing the photos. And what we hope will happen is, as they observe these photos, they will start asking more questions, which will lead to multivariate thinking. And at the same time, trying to ask themselves, well, how do I take these photos and how do I make sense of the data that I need to answer the questions that I'm asking? So this is where we hope that level B students then will start creating or defining variables related to the photos to where they can take measurements for these variables from the photos. So let me give you one more example. I happen to be crazy about doors, front doors. I've always enjoyed looking at people's front doors and seeing the different styles that they might have, different materials that they might use, different colors. So I decided to specifically look at front doors across the world. So here are 4 examples. Now, one thing I then started saying to myself is I have different income levels for each of these families. I wonder what doors might look like within the income levels. Now, the Dollar Street website will allow you to look at the pictures by income level. So where you can define it as high consumption, medium consumption, low consumption. And then I just randomly selected some doors. So here, once again, this might help students sort of compare what's the variability within each of the income levels. And I think what they're going to notice is these doors look very similar within the income levels across the world. So once students at level B have had the chance to kind of independently work with this non-traditional data and define variables and actually collect some measurements from the photos for each of those variables, then by the time they get to level C, high school, we would hope that they develop the skills and awareness of the technology available to then analyze the distributions and possible relationships of these variables. So now, what happens at level C? So let's look at another example. And this time, we're going to look at lizards. But instead of using non-traditional data in this example, instead I'm going to use secondary data. So let's consider this scenario. Let's suppose that in an earlier small study, researchers discovered that lizards in disturbed habitats, now disturbed habitats are those that have human development, tended to have greater mass than lizards in natural habitat. To investigate this further, and this is an actual data set, a biologist, and this particular biologist at the time that she collected this data was a graduate student, a PhD graduate student. She captured randomly a number of individual lizards across 2 habitats on 4 islands in the Bahamas. And she took various measurements on these lizards, including their mass, their head depth, and their hind limb length. So what we might do at this point is we might ask the following statistical investigative question. How can we use a lizard's mass to predict whether it came from a natural or disturbed habitat? So if we were to just randomly select a lizard, well, how could we use these variables to help us predict whether it comes from a natural or disturbed habitat? Now, using the data from this young biologist data set, and notice this is an example of using available or considering available secondary data. The first thing I did was to use the program CODAP to actually create dot plots representing the distribution of the 2 types of lizards, those from the natural habitat, those from the disturbed. So here are the 2 distributions of the mass of the lizards from each of these 2 habitats. Now, typically, In comparing these two distributions, what we would first of all expect our students to do is to describe and compare characteristics such as the shape of the distribution, where do the distributions seem to be centered, the variability within each of the distribution, and also we would look for unusual features. But in comparing the distributions, we would then think about, do we see any separation of the distributions versus overlap? So in terms of thinking about separation, what I might want to look at is to consider, could I draw a cutoff line with these two distributions that I believe would help represent for me a way to separate the distributions to where I could then come up with a classification rule to classify a randomly selected lizard as either from the natural or the disturbed habitat. So in looking at this, just think about where you might draw a line. Where do you see very quickly see some natural separation? Now, I would have my students think about working in groups on this initially, coming up with an initial cutoff line. But I'm going to go ahead today and suggest for you where I think a lot of students will initially draw a cutoff line. And that is, I think they'll draw it around 6 point, let's say about 2.5. And the reason I say that is I see a very clear-cut separation where at that point, all points in the disturbed distribution are completely above the natural distribution. So this might be a trial rule where I classify all lizards with mass less than 6.25 grams as natural. Otherwise, they'll be classified as disturbed. Now you'll notice that once this cutoff line is placed here, I then went back and counted the number of lizards. I now have four quadrants. I then counted the number of lizards in each of these quadrants. So for the natural, using this classification rule, I would correctly classify 81 times. Misclassify, 0. But notice for the disturbed, I would misclassify 55 times, but classify correctly 23. So what we can do with this information then is come up with what we call a misclassification rate. And so we can create a matrix, a classification matrix. And so from this matrix, I can then calculate my misclassification rate, which would be, I have a total of 159 lizards. I misclassified 55. So 65% of the time I classified correctly, 35% of the time incorrectly. So I might then say, well, could I go back and maybe improve my misclassification rate? And what I noticed when I went back is that even though if I move the line down, even though I now no longer would classify correctly all the naturals, by moving the line down to 5, I have picked up all these lizards right here that I am now correctly classifying. And so calculating a new misclassification rate, I now, with this new classification rule, have decreased my misclassification rate by 8 percentage points to 27%. So that now leads me, well, I have all these other variables as well, not just the variable mass. And so I might ask the question, well, can I incorporate another variable to where I can improve my prediction as to which habitat they come from? So I'm going to pick a second variable, head depth, and consider it along with mass. Now, what I would hope that students, especially at level C by this point, would think about doing with this is something that they should already hopefully know about, which is, first of all, just exploring the bivariate relationship of these two variables, head depth and mass. Now, this particular graph I created from the ARTISTAT applets. So what I did, I went in and created a scatter plot to look at the relationship of head depth and mass. And when I created this scatter plot, I saw that there tended to be a moderate, decent linear relationship between these two variables. And I went ahead and had the technology fit a line, least squares regression line. And you'll notice that I'm given an equation here for this least squares regression line. And my correlation coefficient is around 0.64. So yes, it seems like there's a moderately strong relationship between these two variables. Now, how could I then use this to try to, for a randomly selected lizard, think about whether it's from the natural or the disturbed habitat? Well, this one line really doesn't give me as much information as I would like. But what I could do is go back and with the technology, how could we fine-tune the analysis? With the technology, I could actually think about bringing in a third variable now, which is the type of habitat. And what I can have the technology do is color code the points in the scatter plot. So notice the disturbed are the pink, red, the natural are the blue. And it becomes very apparent that they're tending to cluster together. The reds are tending to cluster together, the blues, and that I could, instead of fitting just one line, actually fit two separate lines to the points. And of course, that results in two separate equations. So I would then think about asking students, suppose a randomly chosen lizard has a mass of 3.6 grams and a head depth of 5.5 centimeters. Would you predict this lizard to be from a natural or a disturbed habitat? And how would you use the previous analysis to make a decision? And I would allow students to work as partners or in groups to investigate this question. And what I think is wonderful about this is that there's actually different ways to come back with a prediction. For example, you could simply plot the point on the scatter plot and look to see where the point lies. And what you will notice is that it will tend to lie in one of the particular clusters. Or you could evaluate the two equations of the line. So I could come back and take these two equations and I could plug in my X and my Y, or my explanatory and my response variables for these points, and come up with the predicted Ys. And what you will notice is that you can then think about what is your residual. The residuals, of course, are the error term. Now you'll see 5.5 is the actual Y. So finding your residuals, you'll find that the smaller residual is for the disturbed. So you would predict that it would be from a disturbed habitat. What will also happen is when you plot this on the scatter plot, you will see that the point lies more in the red points than it does in the blue points. So I had three variables originally that I told you that we were going to consider. So what might happen if I brought in the third variable? How could we then think about predicting whether it comes from a natural or disturbed habitat. Well, at this point, this gets a little messier than what we've done previously. But fortunately, with technology, we have what we call classification and regression trees, or what's known as CART. Now, the CART basically works on the same concept as what we were doing originally with the one variable, where we were, for example, drawing these cutoff lines. So what the CART procedure does for you is really what no human is patient enough to do. So at each step of the process, it considers all its available variables and all possible cutoff values. It determines which provides the lowest misclassification rate, and then it splits the data based on that rule. And the process stops when performing a split provides no improvement in the misclassification rate. Now, what happened here, when I used all three of these variables, my misclassification rate was reduced to 18% from the original 35% when I only used math. Now, our hope is that with level C or high school students, that they develop a conceptual understanding of how CART works and they can communicate what a misclassification rate tells us. Classification is a core data science concept, prediction. And we feel that it's really very important that by the time high school students graduate, that they have a conceptual understanding of how classification works. So, in conclusion, hopefully this kind of gives you a sense of some of what the GAISE II document is promoting. And why is the GAISE II document so important in terms of how it might impact your college courses? Well, there's a number of reasons. First of all, it's college courses that actually set the learning objectives for what is expected background-wise when students graduate from high school. So from a college perspective, the K-12 community needs to see what do our students need to know before they enter at the post-secondary level and enter into those introductory statistics and data science courses. The other impact that college courses have in terms of K-12 is teacher preparation. So in order to deliver this curriculum, our K-12 teachers need to be exposed to the same content and the same pedagogy that we need for them to use in training our K-12 students. For many teachers right now, the only statistics course that they might see, school level teachers, before they graduate and go into the classroom on their own, is the intro stat course that they take at your college and universities. So it's very important that those intro stat courses model the content and the pedagogy of what's in the K-12 standards. Now, ideally, we hope that our teachers can take more than just the intro stat course, that they can hopefully go at least 1 to 2 stat courses beyond. And this is where it becomes very important that we have collaboration between our statisticians, mathematicians, and our math and stat educators as to what's needed for our future K-12 teachers. We also have to think about the teachers that are already in the classroom, and that leads to professional development. You'll notice here that I have something called a STEAM, E-S-T-E-E-M. A STEAM is, I would Google this, Holly Lynn Lee at NC State and her graduate students, her team have developed some wonderful MOOCs, as well as just a wealth of resources that they have freely available at their esteemed website that teacher preparation schools and teachers can use as they are trying to get comfortable with delivering this curriculum. So in conclusion, I wanted to give you some links, and I think Pat maybe is going to put these links for you in the chat. Here is the GAISE II link that you can download. If you would like a printed copy of GAISE II, you may actually order it from Amazon. I think it's about $15 maybe if you order it from Amazon. Also, at the end of October, there was an article in the Harvard Data Science Review that introduced the GAISE II document. If any of you happen to follow Alan Rossman's Ask Good Questions blog, Alan was gracious enough to ask me to write a blog this past summer. And so you'll find more there in the blog about the ladybugs and the lizards. Much of what I went through with the PowerPoint is written out in this blog. In the Harvard Data Science Review, I might also mention that there will be 3 articles coming illustrating each of the 3 different levels. So keep your eyes out for that. And finally, to appear very soon, hopefully maybe the next issue of the Journal of Statistics and Data Science Education, there will be an article on what makes a good question. And there will also be a webinar about what makes a good statistical question at the end of April. So if you want to learn more, these are just some sources that you can go to. So that is the end of my presentation. And I'll stop sharing the screen. And if you have questions, I'd be really happy to answer them. Pat?
Yeah, Christine, we did have a few questions that came up during the webinar.
Okay.
The first one, just a quick, what is the difference between statistics and data science?
I wish I knew the answer to that. That is a tough question. I like to say that data science is just statistics enhanced with computing, some mathematical skills. I think that the core concepts that we're trying to get across in our GAISE II document and that I talked about today is that the fundamentals, the foundation, the fundamentals that we're teaching in our statistics courses right now, those are fundamentals for data science as well. The statistical problem solving process and how you go through those 4 components. The questioning that throughout the process that we do. I think for data science, what maybe has changed from what people think of as sort of our more traditional statistics course that we've been teaching is the larger data sets that we're now dealing with. We're dealing with more non-traditional data now, as I mentioned, such as photos, images, sounds, Twitter text, for example. And we're dealing with a lot more secondary data than what we used to deal with. So that affects what types of conclusions you can actually make from the study designs that you come up with. So I wish I could give an answer as what's the difference between the 2. I see that they're really all under the same umbrella. It just sort of depends upon the skills that are needed to work with your data type.
Okay. We got another one here going back to your lizard example. Why might someone want to use the mass of a lizard to predict where it came from?
Basically, this is where the biologists come into play. They're oftentimes very, they may find lizards and they're interested in, the theory is it's better for lizards to be in natural versus disturbed habitats. And so I think they're trying to find ways that if they find these lizards, they actually can maybe use measurements of these lizards to actually predict what type of habitat they came from. So it's kind of one of those science questions of it's important for them to know what type of habitat they're in.
And then the last one, unless more come in, what technology do you recommend for community college students?
Well, I think that depends upon what you're trying to accomplish in your course. Ideally, I think for courses that incorporate a lot of data science ideas, some programming skills would be nice. But I think what we have to realize also, though, is, you know, the sort of the equity issue of what technology is actually available at our different schools and with our different students. There are some wonderful applets out there right now that are free, they're open source, they're web-based, so that will do most everything that we talk about in our document. And I think most everything that you would want to try to accomplish in your intro course and at the K-12 level as well. So there's applets. There's always, of course, R. R is very popular now because it is free. If you can actually have the ability to download R, using R Studio, things of that sort are becoming very popular.
Okay. And along that line, while you were answering that, another technology question came in. Do we or does anyone have any research about students' experiences when they use more than one type of a technology in a intro stats course? And they said, for instance, using Excel, StatCrunch, and CODAP or CODAP.
That's actually a very good question. I'm trying to think. I don't think I can actually name specific articles that I've seen per se. I do think that, at least in my experiences teaching and what I've heard from other people that teach, once students learn one type of technology, like a particular statistical package, those were some statistical packages that you were naming there, it makes it much easier for them to pick up other statistical packages. So, and typically once students learn sort of how to program in one particular language, the logic that they're using for that programming makes it much easier for them to pick up other technology. I would say the thing that I would be most careful about with using a lot of different technologies in one course is it takes time. And I've always, especially at the intro level, I've always felt like that you want to be sure that you don't monopolize your course time with the students getting bogged down with the technology. That you try to think of using the technology as that supplement, that help to get the concepts across, the statistical concepts or the data science concepts, for example.
We got another question. Is there any chance that AP Stats will move to more of a data science focus?
Well, I wish I knew the answer to that question. I think that it's going to need to move to more of a data science focus. I mean, we're actually promoting that that's what needs to happen at K-12, that it needs to move to a more data science focus. And by that, working with the more non-traditional data, working with messy data, secondary data. Now, what College Board will do, I really do not know. I mean, I've been expecting to see that there might be a move to revise the curriculum for quite a while, but I'm not aware that it is going to happen anytime soon.
Chris, I think that's all the questions that have been answered or been asked. I think you handled those all very well. If anyone does have more questions, feel free to put them in. But in the meantime, why don't we thank Christine for her time here and her presentation by maybe a message in the chat. Christine, thank you for your for your good information.
Well, thank you for letting me join you today. It's great.
And I just want to thank Julie and Mark for their support for this webinar and for being here today. We are recording. I will try to get this recording, her PowerPoint and all the links that she's mentioned today. I'll try to get that out to you hopefully later this evening. But if we have no other questions, see, we got a lot of good thank yous coming in on the chat, Christine. Let me just scroll back to see if I missed a question that snuck in between there.
Well, I have really enjoyed seeing the names pop up in the chat of people that I know and friends. And so thank you for coming. Thank you for making time to come and listen. We're really very excited about the publication of GAISE II, and we hope that it's going to have a very positive impact on your classes that you're teaching at your colleges and universities. And like I said, I think there's 22 examples in GAISE II. So if you want to try to get some ideas of maybe potential activities or examples that you can use in your classes, we're hoping that you'll pick up on some of those in GAISE II.
I think I'll wrap it up with, I like this comment. Anytime you come to a webinar or a session and you learn something, it says, thank you, now I have to go down the rabbit hole. Anytime you inspire people to dig in and see what's there and learn it, it's a well done job. So thank you.
Well, I appreciate it. It's exciting. I think there's a lot of excitement ahead for us right now in the statistics world. And there's a lot of momentum going on right now at the state level. Several states are in the process of revising their standards right now, or getting ready to. And many of these states are saying that they want to try to get more statistics and data science standards into their K-12 mathematics curriculum. So I'm of course very excited about that. And I think there's a lot of momentum to do that. But we, of course, need the help of the college and university folks to help guide on that as well.
All right, well said. Well, thank you all for attending today. Be on the lookout for more AMATYC webinars. Those that want a certificate of attendance, when I send out the materials, it will include a link to the evaluation of the webinar. And within that evaluation, you can request a certificate. So that's all for today. Be on the lookout for more webinars coming soon. And everybody have a great afternoon, great evening.
Bye.